Hey everyone, my name is Dan Quintana and this is a companion video for our paper on modelled average Bayesian t-tests, and this is led by Maximilian Meyer, and I'm also a co-author on this paper. This video is going to walk you through some of the benefits of modelled average Bayesian t-tests and how to actually do these analyses, which is a new feature in the latest version of JASP, which is 0.18. Now, Bayesian t-tests are a very useful alternative to frequentist t-tests because it allows you to provides a continuous measure of evidence, and on top of that, it also allows you to look at the relative evidence for a null model compared to an alternative model, and this is something which is not available with conventional t-tests. So we're going to jump straight into the analysis. We have our data set here. Now this data set can be downloaded via the link in the video description. And with this particular data set, we have our condition. So the manipulated condition is called markets and the control condition is called control. And we're looking at the difference or the potential difference in the dependent variable, which is called punishment. Here is the data here. I think it's useful to visualize the data first. So we're going to do that by calculating or by doing a rain cloud plot. So what we can do for this rain cloud plot is first perform a conventional frequentist t-test. It's an independent samples t-test. So we'll click there. Our dependent variable is punishment and our condition is our grouping variable. So we're going to start off by performing a student's t-test, which assumes equal variances, and we're going to make a rain cloud plot. Rain cloud plots are fantastic because they allow you to look not only at the means of the particular groups, but also a visualization of the variances. And here we can see that, at least eyeballing the data, that the markets condition has a much higher variance than the control condition. We're looking at our student's t-test and we're actually given a warning that there's a violation of the equal variances assumption. We can do this formal test here by clicking on assumption checks, and we can do either the Brown-Forsyth or Levine's test. And here we have statistical significance, which is indicative of the violation of equal variance assumption being violated. So in this case, then you should run Welch's t-test. And we can see, okay, so we've done this assumption test, and Welch's t-test is also statistically significant. So we do have a difference between these two groups. So this is how you would do things conventionally using a frequentist t-test. But here you can see a number of steps were required in order to do this. First, we needed to check the assumption of equal variances, and then we had to make a decision. Are we going to stick with students' t-test or are we going to go with Welch's test? Now, the benefit of doing modelled average Bayesian t-tests is you don't have to make this decision. You can look at a number of different models simultaneously, which assume equal variances or assume that variances are not equal. The benefit of model averaging as well is you can also compare models which assume that there's a difference between these two groups or assume there is no difference, and you can also look at the assumption of outliers. Outliers can make quite a difference for t-tests, especially when you have smaller sample sizes. So the sample sizes here between groups are relatively small. So in this case, doing modelled average Bayesian t-tests can be quite beneficial. If you have the latest version of JASP, which is 0.18, and you're looking for this menu here, robust t-tests, if you can't find this, click on the plus button and make sure that this option is selected. Let's click on robust t-tests. We have to do the same thing. It's very similar to what we were doing for our frequentist independent samples t-test. Punishment is our dependent variable and condition is our grouping variable. Now this analysis can take some time depending on the speed of your computer, but you can see things are moving along here with the analysis. While we're doing that, we can actually talk about the model specification preview. Now this shows us the 8 different models that we are looking at the performance of according to the data that we have. Okay, so we'll click here. Let's have a look at this data here. We are, as I said before, we have 8 different models. And what I'm going to do is I'm going to click on this option here of individual models so we can actually see what's happening with those individual models. And click on model overview as well, which can also be very useful. We have 8 different models here. 4 of these models assume there is an effect, and 4 of these models assume there is no effect. Our inclusion base factor is 57.5, so this tells us there is 57 times more evidence for an effect than there is no effect. Again, we can look at this plot that we made as part of our frequentist analysis, and that seems to make sense there. We also have a measure of heterogeneity, or the assumption, or looking at whether variances are equal. And here there is 21 times more evidence for heterogeneity than there is for equal variances here. So that's a good degree of evidence. We also have our 4 models which explore outliers versus our 4 models which suggest there are no outliers. And we can see there's slightly more evidence for there being no outliers in this particular data set, but this number is quite small, nothing compared to the sort of evidence that we're seeing for the presence of an effect or the presence of heterogeneity. As we scroll down, we can look at our model overview and look specifically at the 8 different models that we evaluated. Model 1 assumes no outliers because it's normal distribution, no effect, and equal variances. Model 2, because the t-distribution, which has fatter tails, assumes outliers, no effect, and equal variances. Model 3 assumes no outliers, no effect, and not equal variances. Model 4 assumes outliers, no effect, and not equal variances. Model 5 assumes no outliers, an effect, and equal variances. Model 6 assumes outliers, an effect, and equal variances. Model 7 assumes no outliers, an effect, and unequal variances, and Model 8 assumes outliers, an effect, and unequal variances. And we can actually see the degree to which how much these models contributed to the overall modeled average estimates. And the model with the greatest weighting was Model 7. And again, this was a model that assumed no outliers, an effect, and unequal variances, which fits with the eyeballing that we can look at with this particular plot here, and that this overall weighting contributes to the overall modeled average estimates for the effect size and the standard error. So you can see here with modeled average Bayesian t-tests that we're able to compare and combine and estimate across a range of models which assume the presence and absence of an effect, equal or unequal variances, or the effects of outliers versus non-outliers. We can look at the relative evidence for these 3 factors and also estimate or provide modeled average estimates based on the performance of each of these models. I hope this is useful for you.